guys, welcome to our lecture on ionic compounds. Don't be overwhelmed by all the writing. We make sure that you're actually listening to this and not just writing all of this down.
Okay, so our new unit, during our new unit, we're going to be talking about ionic compounds. Our big idea is that ionic compounds are held together by chemical bonds formed by the attraction of oppositely charged ions. Now, we started to talk about ions just this last couple weeks, but we want to give you a few definitions so this stuff is a little less confusing. First, we have a chemical bond, and that's just a force that holds two or more atoms together. I know that you learned about those in both biology and in middle school probably, so we're going to be talking about ionic bonds today. Then we have the octet rule. That's just the rule that we know where atoms are going to transfer or share electrons to achieve noble gas-like configurations. Remember, they all want to look like noble gases. That's a total of 8 valence electrons. An ionic bond is a chemical bond resulting from the transfer of electrons, okay, the transfer of electrons, whereas a covalent bond is when they are going to be sharing the electrons. A formula unit is just the simplest ratio of ions involved in an ionic bond. That's what we're going to be naming and figuring out today. And then lastly, we have polyatomic ions. And those are groups of atoms with a net charge. So that means most of them all have negative charges. They're all anions except for ammonium. And they are found on the back of our periodic table right up here.
And what that means is that this entire NH4, for example here, has a charge of +1. That entire bonded group of atoms has a charge of +1.
And you can see we have all different types of charges on the back right there.
All right, so a couple of important things about ionic compounds. We said that chemical bonds are forces that hold the atoms together. Here, this is an electrostatic attraction of cations and anions. So when we're looking at the periodic table, remember our cations are going to be formed over here, the +1, +2, and +3 families, right? And really all of these metals. The anions are over this way, right? The negative ions. We know that ionic bonds have very high melting points, and part of that is that electrostatic attraction that's holding them together. It takes some energy to overcome that attraction. So it takes a lot of energy to the point where they have high melting points. What we see happening to form the cation and the anion is that the metal is going to give away its electrons, and it'll form a cation.
So these guys all in here.
And the nonmetal is going to take those electrons and become negative.
These guys over here.
All right? So when you have positive charges and negative charges, they're going to attract each other. When we're writing ionic compounds, the name or the formula unit, they're always written with the metal first. Always have the metal first. All right?
It's like reading a book, right? We're always going to start on the left-hand side of the periodic table.
And then the nonmetal is going to come second. So CaBr2 or calcium bromide. Calcium is our metal. Bromide or bromine is our nonmetal, right? So metal, then nonmetal. And then the last thing is that the subscript indicates the number of the atoms. So in Fe2O3, which is an example of our formula unit, we have 2 iron atoms and 3 oxygen atoms. 2 iron, 3 oxygen atoms, right? We're going to get a little bit into how ionic bonds are formed before we actually see how to name them.
Okay. So, there are 3 different ways that we deal with ionic bond formation. That we deal with ionic bond formation. Remember, this is a transfer of electrons. So we're going to show you this by writing our electron configuration and doing electron dot structure, and then we're going to show you a shortcut, actually. But first, the electron configuration, this is a how-to. You first write the electron configurations for the atoms, okay? This is important. You need to write it for the atoms. So right here, I have written it for magnesium and for oxygen, okay? Abbreviated version is fine. Now, the second part is I show arrows to show the transfer of electrons, okay? Magnesium, we know because it's in the second family or group, it is going to have 2 valence electrons, okay? So these 2 valence 3s electrons are going to be given up to oxygen. Now note that oxygen has 6 valence electrons, okay? So it will go ahead and grab those 2. It will take it happily to fill that P sublevel. And we end up with a magnesium ion looking like neon, right? Having the same electron configuration as neon. And then we end up with a oxide, and it is going to look like it's going to actually also look like neon, but it has this full valence set of electrons now. Do you see how it has 8? That's a 2s2, 2p6. Now, the very last thing we do is rewrite that formula unit. We had one of each of these coming together, so that is going to be magnesium oxide. Okay, for the electron dot structures, what we do is we draw our 2 initial electron dot structures again for our atoms. So we have magnesium over here, and we have oxygen, again, 2 valence electrons, 6 valence electrons. And then you, again, circle our valence electrons and draw our arrows. Magnesium is going to give up both of its electrons, have an overall charge of +2. I don't know if you guys can see that, sorry. And oxygen is going to take these 2 green guys right here. These are its 2 new electrons, have a charge of -2. We also have one of each again because we're dealing with these same atoms and ions. So we are going to be forming magnesium oxide again. Now, this is the shortcut. It's the Now, you guys have to be able to do this and explain this scenario, but this is a shortcut. And that is writing the ion symbol. That's step 1. So I did that right here. You see magnesium I wrote with a 2+ and oxygen with a 2-. And remember, you can tell what kind of charge it will take based on its placement on the periodic table. And then you are going to circle the charge number. So I circled the 2's for both of these, and then I crisscross. And so I give the superscript of the oxygen becomes the subscript of the magnesium, and the superscript of the magnesium becomes the subscript of the oxygen. And then, I didn't draw arrows. Okay. And then lastly, I'm going to reduce that. Remember, our formula unit has to be the smallest ratio. These can both be reduced to, it's a 1-to-1 ratio, same as a 2-to-2 ratio. So I end up with my magnesium oxide. We have another set of examples on this side, and Ms. Frankovic is going to draw the arrows because I forgot to up there. So you can see calcium, again, is going to have 2 valence electrons, but you can see that chlorine actually only needs 1 valence electron based on where it is on the periodic table. So if I have 2 electrons I need to give up, but I only have chlorine that is willing to take it, I'm going to end up needing 2 chloride ions to take both of those electrons. So I wrote that electron configuration twice. Now we ended up with our calcium ion, again, looking like our noble gas, argon, and then our 2, that's what this big coefficient represents right there, 2 chloride ions that have our full valence shell. And we end up with what we call calcium chloride. Now you can see, second example, we just drew 2 electron dot structures for chlorine because we need 2 of those chloride ions in the end. So we have calcium with our 2 valence electrons, each giving one of our chlorine atoms an electron, and we end up with calcium with a 2+ charge, chlorine with our chloride with a 1- charge, but we have a total of 2 of those, so that's what and that becomes our subscript, and so we end up with calcium chloride.
Subscript right there.
Okay. So again, crisscrossing and reduce, wrote the ions in their original charges based on the periodic table, or what charges they are going to be, and then we circled, crisscrossed, and we reduced. We don't need to include that 1 anymore because we just assume if it's there, it's a 1. So we end up with calcium chloride.
All right. So now that we know how to write the ionic or the formula units, we're going to look at how to name ionic compounds. Do not be overwhelmed. All right, so this is what we call ionic bond nomenclature. The first type that we're going to talk about is called binary compounds. Now, if you think about binary, bi means 2. All right, so, it's from
the examples that we.
The examples from the last time has that. All right, but we have only 2 elements in the compound, right? Bi means 2, only 2 elements in the compound. All right, So MgO was one of our examples. Now, within binary compounds, we have two different types, type 1 and type 2. Again, don't be overwhelmed. Type 1, as you would assume, the metal has only one possible charge, all right? So that's all of those that we've predicted from the periodic table and that we have labeled there, the charges, all right? Those only have one possible charge. Those ones are pretty easy to name. We're going to have the metal name plus the nonmetal, where we drop the ending and add "ide." Okay?
It's going to be one of those guys right
now,
there.
Remember, magnesium, or the metal comes first, then the nonmetal. MgCl. We're going to name the metal magnesium. Okay? Then we're going to name the nonmetal, but drop the ending and add "ide." So magnesium, and this becomes not chlorine, but chloride. Right here, the metal, we just name it aluminum. The nonmetal, drop the ending and add "ide." So oxygen becomes oxide, aluminum oxide. Okay? Now, type 2 is a little different. Type 2 metals have multiple possible charges. These are not ones that we predict from the periodic table. We have to find them on the back side of the periodic table. And Ms. Thomas will show you those.
Right here.
Right?
And you'll notice they are all our transition metals.
Right? So, they have multiple charges, so we have to use that back of the periodic table to actually name these. These are named the same exact way as type 1, with the exception of adding in a Roman numeral that indicates the charge of the metal. Okay?
So you can see, what are we doing? Yeah, iron 2 plus is, or iron, yeah, 2 plus is going to have a Roman numeral 2 in parentheses right there.
All right, so FeO. Using that crisscross method, we can figure out that iron here has a 2 plus charge. So instead of just iron oxide, this needs to be iron 2 oxide to indicate that that iron has a 2 plus charge. Versus Fe2O3, we know that Fe here has a 3 plus charge. So we need to indicate that charge of the metal here with Roman numeral 3. So both of these might look like iron oxide, but one is iron 2 oxide, the other is iron 3 oxide. Now, that's binary. 2 elements in the compound, that's it. What if we have 3 or more elements in the compound? All right, the way we have this is if we have a polyatomic ion. Now remember, those are the ions that, they're a group of atoms that have the overall charge. Okay, so like NH4 with a +1 charge. The whole group of atoms has a charge. We're going to look at the back side of the periodic table to name these. Okay, so you're going to find these on the back of the periodic table, and all you have to do is look at the name that's given. All right? So we're going to find the names and charges back there. Our hint is that the polyatomic ions typically end in -ate or -ite. All right? Now, how we name these. Again, the metal stays the same. Every time, we're just naming the metal as it is. Right? So the metal stays the same, and then the polyatomic anion, we're going to just look at the back of the periodic table. So, NaNO3. Na is sodium. NO3, we need to find on the back of the periodic table. So we find it, and we look to the right, and we see that it's nitrate. Okay? NaNO3, sodium, nitrate. K2SO4, we're going to name the metal just as it is, potassium. SO4, we find it on the back of the periodic table. SO4 is sulfate. SO4, 3 minus, sulfate. 2 minus. We have potassium sulfate. Last one, AlHCO3. We're going to name the metal just as it is, aluminum. And then we find this polyatomic anion, which is HCO3 with a -1 charge. And we see that it is hydrogen carbonate. So we have aluminum, hydrogen carbonate. Aluminum, hydrogen carbonate. And that's it for naming, all right? Every time the metal stays the same. What's changing, really, is that nonmetal. Nonmetal plus ide, nonmetal plus ide, and then the easiest of all of them, look on the back of the periodic table, all right? So that's it for ionic bonds. We're going to look at other kinds of bonds in our next video, but here's our transferring electrons to form bonds. Thank you.